All right, welcome again to what I can only hope are good choices. Mic check 1 2 1 2. Looks like might be able to. It's a little bit okay. That's probably a bit better. All right, so this I can pretty confidently say is a good choice. We're gonna keep on going with the LPIC-1 exam. I just want to revamp my skill sets so that I'm more valuable towards remote work. A lot of the stuff I'd been doing, enterprise, data center, ISP, that's networking. You're dealing with routers and switches. You're dealing with actual physical gear. So, like in my experience, I would like most of my career, I only had really one job where it's like, yeah, I had to go into the data center and working remote was legitimately for valid reasons not possible, but like every other job I've worked, it would have been totally fine. It's just there are certain fields that lend themselves to that better than others, and I feel like networking as a whole is especially like enterprise ISP service provider isn't really one of them. So I think like cloud lends itself better. I think just having a broader generalist skill set and kind of worrying a bit less about automation is really important for me now as well, because then you have your toe in various you know you have a broader sense of like what you can actually do as a professional and make money in. And if there's something that is that dream job that you're looking for, in my case something that allows you to work remote, location independent, you would never even hear about that if you didn't have a generalist skill set and it fell into a skill set that was not addressed in your specialty. So having that generalist skill set is really important, and that's one of the things I lack. So the LPIC I think is good for a generalist, because no matter what you do in tech, you will be using Linux to some capacity. So really become a professional Linux user, power unit Linux user. Really understanding that, I think, is good for both a specialist and a generalist. And then the other thing that is good for both a specialist and a generalist is just being able to code at a high level. So yeah, I've got everything worked out. Technical development, my certifications, the LPIC, I think makes sense. I think a DevOps cert makes a lot of sense as well. Can always go up, but then we're getting into the specialist versus generalist again. So lots of places to go. I think the next one I'd want to do is the PCAD, because I just want to get my core skills up, and I might even want to do like a just like algorithms, or like general job interview training, because I think that could go a long ways. All right, so last video we did part 1 of 104.5. It's another mega lesson which will happen in multiple parts. So we learned all about permissions, which is something I know I've used quite a bit, just kind of in a bohemian style. So that means kind of like in a self-taught style, and just like basically taking things as they come, and like learning the hard way, where you just do it without really knowing what you're doing and why. I've had a lot of those kinds of experiences with Linux permissions, so it's good to dive in and go to a professional learning institute to really get a better intuition for Linux permissions. All right, so in this next section is default permissions. Let's try an experiment. Open a terminal window and create an empty file with the following command. All right, so let's do that. I'll pull up my lab. Okay, so and I'll do it in the home. Let's do a new folder. So we're gonna do mkdir. We're going to do permissions lesson, and then we're going to change it to it. All right, and now it's easier to delete. You can see my home is kind of cluttered, and you know, this is like a production lab for me for doing a lot of my GNS stuff, so it's like having a cluttered home drive kind of doesn't make a lot of sense. So it's good habit to have things in a parent folder that is not going to be shared with unrelated things. All right, so let's do touch test file. All right, so now let us look at the permissions for this file. It may be different on your system, but let us assume they look like the following. Okay, so let's see what it looks like on mine. So LH, human readable long form, so we can see those permissions. And yep, it's quite a bit different. Well, it's not that much different. The only difference is the user group for my system allows for read access by default, but that's the only difference. Sorry, for write access by default. The permissions are rw-r-r-. Read and write for the user, and read for the group and others. In my case, it is read and write for the user and the group, and then read for others. Or 644 in octal mode. And let's think about what it is for mine in octal mode. So we know that these parts are going to be the same, and we know that this first part is a 6. So there we go. That's an easy way to know it. 664 is what mine's going to be. And the other thing we could do to come up with the octal mode, and I was planning to do this in the last video, but you know, if you don't know basic binary at this point, that is kind of a basic fundamental number literacy math concept. Just, you know, I'm sure there's some basic binary. Just go to like Khan Academy. I love Khan Academy. So you type in like Khan Academy binary, and there you go. So this is like a computer science concept. It's just like, you know, when we count numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, in order to represent the number 10, we need another place. We need 2 digits instead of just 1. So binary is a system where in order to represent the number 2, you need to use 2 digits and just 1. So it's only 0 and 1 are the only numbers you get to represent values, and it's just another way to represent numerical values. So here's a good one: Khan Academy, decimal numbers. You know, just read this, do some exercises, watch the video. Should be good to go. Yeah, let's think of it that way. So we've got our 3. So we've got our octal numbers here. So let's see here. So octal mode. So we've got an octet is this. Okay, but we're only going to need to worry about this much. Okay, and then we know that what these numbers, and we know this from the prior lesson in the last video. So what these numbers represent is this first number represents for the user read permission. So if read permission is off, it's a 0. If read permission is on, it's a 1. In my case, the read permission was on. Same thing for write permissions. If it's off, it's a 0. If it's on, it's a 1. In my case, it was a 1. And same thing for execute permissions. A 0 for off and a 1 for on. Mine was a 0. Okay, so let's figure out what this number is here. So we know that these are binary numbers, so that we know that in order for it to represent the number 2, we need 2 digits. So this represents the number 2 here. because the twos place is on. So to represent the number 1, we would have it here. So this is the ones place. This is where we can represent a 0 or a 1. Now this is the twos place. This is where we represent either the number 2 or the number 3. And now this is the fours place here, where we can represent the number 4 like this. And we need 3 digits to do that, because each digit can only represent a value of 0 or 1. So, but they do so in their place. So in the fours place, we represent a value of 4. Now in the twos place, we turn it on and we represent a value of 2. Now in the ones place, what do? Well, we leave it off because this is the execute permission and we don't have that. So to get this, we know that the fours place is on, the twos place is on, and the ones place is off. So 4 plus 2 plus 0 equals 6. And that's how we get the octal number 6, is because we're expressing these in binary values, and then we convert the binary to the decimal value, and the decimal value is what we use for octal mode. All right, so now try creating a directory. All right, so let's do that. Okay, and now we need to do a ls-lh. We need to do this d so that we see the permissions for the directory itself and not the files within the directory. All right, so now the permissions are and we see we leave off the d. So it's read, write, execute for the user, the owner of the file, then read, no write permissions, and then execute for the group, and then read, no write permissions, execute for everyone else. So the same as for the group. Read, write, and execute for the user, read and execute for the group and others, or 755 in octal mode. All right, so now let's see what I have, and let's convert it to octal mode. So let's move it to a notepad like this. All right, and then we'll separate it into each of the permissions. So we can see for the user, we're allowing read, write, and execute. For the group, same thing, read, write, and execute. And then for the others, read, write, and execute. So now let's convert it to octal mode. All right, so which digits are on or off? So for this one, we've got all of them on. For this one, we've got all of them on. And for this one, we have all of them on except for write. So now we can add them up. So this is the fours place is on, the twos place is on, and the ones place is on. So 4 plus 2 plus 1 is 7. And this one is the same, so we don't even have to do the math on there because we know it's the same. Now this one, the twos place is off. So it's going to be 7 minus 2, it's going to be 5. So the permissions here are 775, which is different from the permissions in the learning material, which are 755 in octal mode. So no matter where you are in the file system, every file or directory you create will get those same permissions. Did you ever wonder where they came from? I actually do wonder where they come from. They come from the user mask, or umask, which sets the default permissions for every file created. You can check the current values with the umask command. Okay, so here we go, umask. So these are the default permissions. Now, one thing, hopefully I'm not the only one to just notice here, is it looks like we have an extra bit here. I'm not sure why we have that, because permissions are a series of 3 digits, not 4. Um, so these are the default permissions for every file. Let's see if it's, now obviously it's going to be different from mine, but let's see what it is. Okay, so it's quite a bit different from mine. For the most part, it's the same. We've got 4 digits just like there, but we have a 0 instead of a 2 in the 1, 2, 3, third digit. But that does not look like exactly RW dash, R dash dash, R dash dash, or even 644. Maybe we should try with the dash capital S parameter to get an output in symbolic mode. All right, so let's try it. All right, that looks better. That looks familiar to what we saw up here. Those are the same permissions our test directory got in one of the examples above. But why is it that we created a file in the why is it that when we created a file, the permissions were different? So I didn't even notice that. So we can see here's the default permissions, but directories actually, but files. So the directory has that, but the file actually has different permissions. So where do they come from? Well, it makes no sense to set global execute permissions for anyone on any file by default, right? Directories need execute permissions, otherwise you cannot enter them, but files do not, so they do not get them. Hence the rw dash r dash dash r dash dash for a file. And it's the same for me. No execute. We do have that extra right, but it looks like the same concept applies. Execute is not given out by default for files the way it is for directories. Besides displaying the default permissions, umask can also be used to change them for your current shell session. For example, if we use the command, and I'm not going to do this because this might mess things up, but this is a way you could change the default permissions system-wide, so please do that at your own peril, preferably not on some production work system. So, for example, if we use the command, every new directory will inherit the permissions, and so this is for directories, and every file will get the same thing, except the execute will be turned off. So every new directory will get read, write, execute, and then dash, dash, dash. But every file will get the same except for the execute. It will get read, write, dash, and then dash, 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 as they do not get execute permissions. If you repeat the examples above to create a test file and test directory and check the permissions, you should get, so if you repeat them after you change the default permission settings, you will get the new default permission settings once you create them. You won't get the new, so they won't show up. So if you change the default permission settings and then run these again without deleting them and recreating them, then they'll have the permission settings from the old default. It is only after you recreate them is when the default applies. It does not go back and change existing permission settings. If you check the umask without the dash capital S symbolic mode parameter, you get umask 007. Okay, great. We're going to learn about this. Very confusing because we get 4 digits instead of 3, and we see here this 7 doesn't appear to be a valid digit for one of those digits. The result does not look familiar because the values used are different. Here is a table with every value and its respective meaning. And I'll take a break. I got to change my posture, and I'll be right back. All right, I'm back, so let's keep going. Let's take a look at this table. So we've got the columns, value, permission for files, and then permission for directories. So that's why we've got that extra digit, is because we're setting the defaults not only for directories, but also for files. So we do need an extra Oh, wait, what? Okay, so we can see that the values correspond to the permission settings for files and directories. Um, they're going to be the same except where execute is granted to a directory, it will not be granted to a file. So we can see none of the permissions for files include the execute. Um, and some of them do and some of them don't for directories. So where they do, we have a different setting for files that does not include the execute, and where they do not, we have the same value. So as you can see, 007 corresponds to read write execute, uh, 000, and that's because the first digit, the 0 is read write execute for directories. The second digit is also a 0, and then the last digit is a 7, which is nothing. Exactly as we requested. The leading 0 can be ignored. All right, it's time for the AI, because like why? That's so like upsetting to me that there's a leading 0. Okay, so let's ask the AI. Okay, and I'll say it's upsetting to me that there's a leading 0. Why is this included if it's just meant to be ignored? All right. Yeah, I love the AI for this.
The inclusion of the leading 0 in octal notation is a convention in Unix-like systems to represent numeric values in base 8. While it might seem unnecessary or confusing, it's a consistent part of the Unix tradition.
Oh, that makes sense.
Here's why it's included. 1. Consistency. Unix and Unix-like operating systems have a long history of using octal notation for specifying file permissions and other numeric values. The leading 0 is used to indicate that the number is in octal, which helps maintain consistency within the Unix environment. 2. Historical reasons. The inclusion of the leading 0 in octal notation dates back to the early days of Unix. It was a design decision made by the creators of Unix, and it has remained a part of Unix conventions ever since. 3. Clarity. While it may seem unnecessary, the leading 0 actually serves to make it clear that the number is in octal notation. In Unix, there are different notations for representing numbers: decimal, octal, and hexadecimal, and the leading 0 helps distinguish octal numbers from decimal ones. 4. Tradition. Unix systems have a strong tradition of adhering to established conventions, and the inclusion of the leading 0 in octal numbers is one of these conventions. Deviating from such conventions could introduce inconsistencies and potential confusion for users familiar with Unix practices. While the leading 0 may appear unusual to those who are not accustomed to Unix conventions, it's an integral part of how numeric values are represented in the Unix environment. It's not meant to be ignored, rather, it's there to indicate the base in which the number is expressed, octal, and it's an essential aspect of Unix's historical and ongoing design principles.
All right, so I'm actually in the. I had to take care of something while I was going, but yeah, okay, that makes a lot of sense because, this is not like if you learn about computers, they come like based on like the hardware, based on like the disk and everything, like they're already like pre-partitioned, like how much data they can represent. So like you'll never have it like by nature of it being an octal number, it's going to be this is called like a nibble or a byte. So they're just not using the full byte, but that doesn't mean that the full byte is not existing and allocated. So it's like it's like significant digits. You can almost think of it like if like for example, if we have a value of 12.0, like the 0 it's 0. Like, we could just write 12, right? But like, it's significant that it is point 0 because we're measuring to that level of precision. So we need to know that if it were a 4 or whatever it happened to be, that 4 is, it's not superfluous. It matters in the measurement. So like, that's why you have like, you include significant digits, even if they can be shorthanded, because it's significant to know that they actually are 0 and you're not just rounding or leaving them off in some way. So it's significant to know that these are octal numbers, meaning that they come in bits, and they come in bits, nibbles, and bytes. All right, so yeah, this makes sense. So the next one is special permissions. I'm gonna pause it and be right back. All right, I'm back after a substantial break. But I remember what we learned about. We learned about the default permissions, so let's move on to the special permissions. Besides the read, write, and execute permissions for user group and others, each file can have 3 other special permissions. And I'll do a mic check because I've been away for a while. Mic looks good. Which can alter the way a directory works or how a program runs. They can be specified either in symbolic or octal mode and are as follows. All right, so the sticky bit, which should have a T. Okay, that's interesting. And the T comes, so the T is one of the options you can have instead of a dash. All right, so the sticky bit, also called the restricted deletion flag, has the octal value 1. And in symbolic mode, that's interesting, octal value of 1. I would think that execute has an octal value of 1, like a yeah. So I'll ask the AI about this. And in symbolic mode is represented by a T within the others permissions. This applies only to directories and has no effect on normal files. On Linux, it prevents users from removing or renaming a file in a directory unless they own that file or directory. Directories with the sticky bit set show a T replacing the X on the permissions for others on the output of ls-t. Okay, so it looks like it's only in the others it shows up. So ls-l we can see shows it here. So let's go ahead and ask the AI about this. Okay, and then the question I have for the AI is, isn't execute or X or doesn't execute, aka X, have an octal value of 1? Yeah, so okay.
I apologize for any confusion in my previous response. You are correct, I made an error in my explanation. The octal value for the execute permission X is indeed 1, not the sticky bit.
Oh.
Thank you for
Well,
pointing that out.
No, they're saying that
To
it
clarify, execute permission, X, has an octal value of 1. The sticky bit has an octal value of 1 as well, but is represented differently in the permissions. In the example you provided, The T in the directory permission
They both have
signifies
it.
the presence of the sticky bit, not the execute permission. The sticky bit is indeed represented by the octal value 1, just like the execute permission, but they serve different purposes and are represented differently in the permissions display.
Okay, it looks like it's going to explain it here. So in octal mode, the special permissions are identified using a 4-digit notation. Okay, so that's another reason why we got these 4 digits for the UMask. There are special permissions that use the 4th digit, with the first digit representing the special permission to act on. For example, to set the sticky bit value 1 for the directory another underscore directory in octal mode with permission 755, the command would be change mod, and then yeah, we can see how. I mean here it's not exactly the same here because, well, yeah, it is. No, it is. But it corresponds to the chart for here, so no, it's not exactly the same as what you see here. Oh, you know what? Yeah, it is. No, it's exactly the same. It's exactly the same. Is it or is it not? It is. It definitely is. We can ask the AI about that. I guess I'm confident enough that this is the same as what you have here, and that's why that's part of why there's an extra one here and there's not there, because here you just drop the leading 0. Here we're keeping that in for clarity. Yeah, for example, to set the sticky bit value 1 for the directory, so here we go. Now we have the 4 digits, and we can see the T is there. All right, so here's another special permission. It's set GID. Set GID, also known as SGID or set group ID bit. So not to be confused with globally unique identifier, GUID. This is something different. It's the GID with no U, and it's the group ID. So set SGID stands for setting the group ID bit. So set GID, also known as SGID or set group ID bit, has the octal value 2, and in symbolic mode is represented by an S in the group permissions. This can be applied to executable files or directories. On files, it will make the process run with the privileges of the group who owns the file. When applied to the directories, it will make every file or directory created under it inherit the group from the parent directory. Files and directories with SGID bit show an S replacing the X on the permissions for the group, because remember this is set group ID, on the output of ls-l. So here we go. We've got ls-l of this special file, and then we've got owner, then we've got everyone else, and we've got the group here, and we should notice, there's an S. I thought there was only R, W, and X. There is for standard permissions, but for special permissions, we have the T that we saw earlier, which could go in the group, and we also have the S. Sorry, in the others. The others portion of the permission settings. And then we have the S for a special permission that applies to the group. So to add SGID permissions to a file in symbolic mode, the command would be, so symbolic mode means we're going to use symbols instead of octal numbers, and the symbols represent the permissions and what we're going to do with them. So here we go, chmod, G for group, and then we're going to add the special S permission. And then it goes to the group. It knows that because of this G here. And there we go. The following example will help you better understand the effects of SGID on a directory. Suppose we have a directory called sample_directory owned by the user Carol and the group users with the following permission structure. So ls-l LDH sample underscore directory. Okay, so it's a directory. Here's its permission settings. We don't have any special permissions or anything. Now let us change to this directory and using the command touch, create an empty file inside of it. The result would be, there we go, touch file. There we go. And the result is that because the UMask default permissions are set up so that these are the default permissions assigned to a new file. As we can see, the file is owned by the user Carol and group Carol. But if the directory had the SGID permission set, the result would be different. First, let us add the SGID bit to the sample directory and check the results. So sudo chmod, and then for the group, we're going to add the special permission to the sample directory. So now we need to do the D because we want to see that the settings of the directory itself. We could also do a -A and look at the self-referential character for the directory, the dot, and see the permissions there, and those would be the same. But this you get a more clear indicator. So we can see we added that special permission there. The S on the group permissions indicates that the SGID bit is set. Now we will change to this directory and again create an empty file with the touch command. Alright, so now that this is a directory that has special group permissions, we're gonna change to it, create an empty file, and then take a look at the permissions on the empty file. Now this is interesting. It looks like it's the same as it was, even though it has the folder it belongs to has different permissions. But we do see something that looks kind of interesting. We noticed when we did that here, we had the user group be assigned to Carol, even though the user group of the folder was assigned to users. But now, with this special permission setting, we see that the user group of the folder users is now the automatic default user group for the new file in that folder. The group who owns the file is users. This is because the SGID bit made the file inherit the group owner of its parent directory, which is users. So you can see that's really useful. I really think I'm surprised this isn't like default behavior. What? No way. I refuse to believe it. All right, let me check my ChatGPT. Maybe it logged out or something. No, it looks good to me. Not sure what's happening. Oh, anyone wanna? Here, I'm gonna put these on my. I'm gonna put these links in my doobly-doo. I think it thinks the technical term. It's called a doobly-doo. There's no doubt about that. But if anyone wants like a quid pro quo or just like oh, well, I mean, you can see, well, I'm gonna put it in the description so you'll have it by the time this comes here. So yeah, so if somebody wants like a discount or a free trial ChatGPT, just use one of these codes. I'll have them in the description. Okay, so let's see the I am kind of interested in asking at least one question here. Okay, not sure what happened to my ChatGPT, but it looks like it's good. So my question is this special permission setting of and the special permission is S that makes it so that files created within a folder automatically get assigned to the group that is assigned to the folder seems like a critically important permission setting that would have common and widespread use. Is this true? Is this true? Please tell me. If so, please not. If so, please tell me some real world use cases. If not, please explain to me why not to use this commonly. Why is this a special permission and not the default thing that happens to files that are created in a folder? All right, let's hear the nice man, kind of a Morgan Freeman, I would say, voice. Close, kind of close. Like a sleepy Morgan Freeman, like just got out of bed or something.
The SGID, set group ID, permission is indeed a useful and important feature in Unix-like operating systems, but it is not the default behavior for several reasons.
Definitely Morgan Freeman.
Here are some real-world use cases and explanations for why SGID is not the default. 1. Group collaboration. One of the primary use cases for SGID is in scenarios where multiple users or processes need to collaborate on files within a directory while ensuring consistent group ownership. For example, in a software development environment, a project directory may have SGID set to ensure that all newly created
so
files
that's what
within
I'm
the
thinking
project are owned by the project's development group.
Boom. Yeah, you need that.
This simplifies access control and sharing among team members. 2. Shared directories. In shared directories where multiple users need to access and modify files regularly, SGID can be useful. For instance, in a university's coursework directory, professors may create directories for their classes with SGID set to the respective course group. This way, all files created by students within the directory automatically belong to the course group, facilitating grading and collaboration. 3. Consistency and security. SGID helps maintain consistency and security within a directory. However, it is not the default behavior because it may not be suitable for all directory structures or use cases. Some directories might need more specific or granular control over group ownership. In cases where files should belong to individual users or different groups, manually setting permissions is more appropriate. Default behavior aims to minimize unexpected results. If all directories had SGID set by default, it could lead to unintentional data exposure or security risks. For administrative control, setting SGID is an administrative decision, and administrators typically use it where it makes sense. It's important to have control over whether new files inherit the group ownership of the parent directory or not. In summary, while SGID is a valuable permission setting with real-world use cases, it is not the default because not all directories require this behavior. The default behavior aims to be more conservative and allows administrators and users to make intentional decisions about file ownership and access control. SGID is a powerful tool, but like other permissions, it should be applied thoughtfully to meet specific needs rather than being a universal default.
Yeah. Okay. So yeah, here are some real world cases and explanations for why SGID is not the default. So for group, yeah. So if, yeah. So it's just it's not the default, even though it's super useful because, and that's what people really like about Linux is like, it's like a set of Legos. Like you can put it together the way you want. So like, if it comes all put together, you might not be trying to make the Millennium Falcon out of Legos. So like that's one of the good things about Linux. It's one of the like trade-offs where like, like Windows comes a certain way, probably, some things are more constructed and put together the way like best practices would be or whatever, set up in advance. And that could be a perk or a feature or a bug. But definitely remember this, because there are a lot of real world scenarios where you want files to automatically be assigned to the appropriate permissions group without having to go and do it individually. And that's what this was. All right, so the next section is set UID. SUID, also known as set user ID, has the octal value for and is represented by an S, just like the other one, on the user permissions in symbolic mode. It only applies to files and has no effect on directories. Its behavior is similar to the SGID bit, but the process will run with the privileges of the user who owns the file. Files with the SUID bit show a S replacing the X on the permissions for the user on the output of ls-l. So ls-ld for directory. There we go. So now instead of the X, we have an S. You can combine multiple permissions on one parameter. So to set SGID value 2, okay, and value 2 in this first bit, that's usually just left off. That's abbreviated. So value 0 is the default, and it doesn't even display typically. Value 2 is to set the SGID. Value 4 is to set the UID. Value 1, as we learned about, is to set the sticky bit, which makes it so that... Oh, does it not explain? Oh, which makes it so that users cannot remove or rename a file unless they can own that file or directory. Okay, so it's kind of like revoking write permission to the file itself. So like you can think of the write in here as like the contents of a file. So you have the permission to read the contents of a file. You have to have permission to make changes to the contents of a file. But if you want to deny someone the permission to remove or rename the file itself, you can use the sticky bit, which is the first of the 4 bits in the octal mode identifier of the permissions. If you set that to a 1, then it will be so that the sticky bit is on, which prevents users from removing or renaming a file in a directory unless they own that file or directory. Okay, so that is 1. We also learned about the value 2, which is the SGID, which makes it so that when you create a file within a folder, the user group of the file is automatically assigned the same user group that was assigned to the folder in which it resides. And then the SUID value 4 in octal mode for the script test.sh. So then what that does for the octal mode um, it will run the file with the privileges of the user who owns the file. I guess regardless of who. So even if you're the other, it will give you that right permission as long as there's an S there, which is kind of interesting. So you can combine multiple permissions on one parameter. So to set SGID value 2 and SGUID value 4 in octal mode for the script test.sh with permissions 755, you would type chmod 6 because we're setting both at once. So 2 plus 4 equals 6. Then 7 because we're setting the user permissions to read, write, and execute all bits on. 4 plus 2 plus 1 is 7. And then here we're setting 5. So it's an odd number, so we know that the last one is on. And we also have the 4's place on, so we have the middle place off, so we have read and execute permissions. And same for the other as well as for the group, same set of permissions, read and execute. And the result would be, as we saw, read write S for, that's what the 6 is for. Then okay, so here's the special permission. Oh right, sorry. This is because it's the 2 and the 4, so we'd have the S in both of them because we have the value of 6 here. It means that both of these are going to get an S, and then I was correct about the last one. So tip, if your terminal supports colors, and these days most of them do, you can quickly see if these special permissions are set by glancing at the output of ls-l. For the sticky bit, the directory name might be shown in a black font with blue background. The same applies for files with the SGID yellow background and SUID red background bits. Colors may be different depending on which Linux distribution and terminal you use. All right, so let's try to see that colorization. That sounded interesting. Okay, so I'm in the permissions lesson. That looks good. So let's assign some special permissions. Let's do a test.sh. So touch test.sh, and then we'll do chmod, then 6 755 on test.sh. All right, and then we'll do a ls-lh test.sh, and there we go. Now we've got it highlighted in red. So for the sticky bit, the directory name might be shown in a black font with blue background, so we don't see that here. The same applies for files with the SGID. So here we would get a yellow background, and the SUID, so red background bits. So we have a red background bits. We have both of these, so it looks like it just took the other one. So let's take that one away. So how would we do that? Any guesses? 3, 2, 1. So we change the first bit, and we make it so that the SUID bit is off. So the SUID has an octal value of 4. Yep. So 3 plus 4 is 7. So we have to deduct 4. So now we have a 3. Yep. So 3755. All right, and let's take a look at that. There we go. Now it's in yellow. So let's change it to be with a blue background. So to do that, we would need to set the sticky bit. So we set this to a 1. Take a look at it again. Okay, and now it's in a green background. We do see that the sticky bit is set correctly, and we don't have any other special permissions assigned. So, it just depends on your colors may be different depending on which Linux distribution and terminal settings you use. So this one was different for me, but we can see it is green. Let's get rid of special permissions on it and see what color it is then. Okay, so without any special permissions, it is in green. Typically, it's in green if it has execute. Let's get rid of execute just for fun here. So this will be a 4, 4, 6. We're just deducting 1 from each of them, and then we'll turn on the sticky bit special permission. Okay, and now we can see. Oh wow, that's fascinating. Now we have a capital T. Okay, we're in. We went beyond the scope of the course. We're now floating through space with no oxygen tank. So let's just move on to the guided exercises and hope this never is shown again, especially not on the test. All right, so guided exercises. Create a directory. And one thing we might be able to do is if you do like a man on Chmod, you might be able to get help on permissions. Yeah, so we can see all the everything we learned, the symbolic. Probably see a description of the octal scheme. So the help menu, the manual pages are always good to get used to looking at. All right, so let's try to get through all the exercises. That would be absolutely amazing at the hour mark, but closing this out would be a dream come true. All right, so guided exercises. The first exercise is create a directory named empty dir using the command make dir empty dir. Now, using ls, list the permissions for the directory empty dir. Okay, so let's do that. So we're going to do it in this permissions lessons. Let's remove everything that's currently there. So we're going to rm-r. So we're going to remove the directory as well. Okay, and now we've got this empty. So we'll do the first part of the guided exercises, which is to make a directory. So we do mkdir, and then the directory name, emptydir. All right, so now using ls, let's list the permissions for the directory. So if we look at our present working directory, we are in the parent directory to this, not the directory itself. So if we do an ls, typically we would see the contents of the directory. If we want to see information about the directory itself, we need to do a -d. Let's also throw in a -h to make it human readable. And then we do need the L as well so that we see those permissions. All right, and to prove it, if I take away the L, now we just see the directory and we don't see the permissions. All right, but there we go. List the permissions for the directory. Got them right here. All right, so second, and maybe we can look at the answer for this. I'm not sure. Okay, yep, so you need the -L, you need the -D. -H is optional, but it's totally fine. But yeah, I got full credits for that. So add the -D parameter to ls to see the file attributes of a directory instead of listing its contents. So the answer is, there you go. And that's key. If you want to see information about the directory itself and not its contents, you need that -D there. Or you need to at least do a -A so that you can use the self-referential dot to get them that way. But the cleanest way, and the way that is the most true on the exam, most likely, is to include -D. All right, so number 2, create an empty file named empty file with the command touch empty file. All right, so let's do that. And we're going to make it outside of the directory. emptyfile. All right, so now using chmod in symbolic mode, add execute permissions for the owner of the file empty file. Okay, so we have to do chmod And we're going to do it for the owner, which don't get confused. It's not the O, it's the U for user. And then we're going to add a permission like that with the plus sign. And it's going to be execute permissions, which is with an X. And we're going to do it for empty file. All right. And, but we're not done yet. Remove, write, and execute permissions for everyone else. Do this using only one chmod command. So the question is kind of bad because everyone else is basically like a colloquial way of saying those in the others user group. But, it's kind of a bad word to use because, like, do they mean for the group as well? Like, that would constitute everyone else, but I assume they mean it just for the O group. So let's do it for the O group. So we're going to do minus WX. Okay, and we have to use a comma if I remember correctly. There we go. That looks good to me. All right, so that's my answer. I'm sticking to it. Let's see what the true answer is. And this is where we'll see if it was a trick question or not. All right, so think about it this way. For the user who owns the file U, add, so yep, that's what the U stands for. Don't get that confused with the O, which stands for others. Add a plus sign, which is what I did. Execute permissions. So U plus X. Got it. For the group and other users. Okay, so yeah, this is where it's kind of like a Cisco exam where they're coming after your your basic. You have to translate it to Chinese first, if you know what I mean, and then once you've successfully translated it outside of the actual technology you're learning, then you have a chance to get it right or wrong. So like, I interpreted this to mean applying the others group and then leaving the group permissions the same. But what they meant is for both the group permissions and the others permissions, change it to grant or to remove, write, and execute. So I would have done it differently if I knew that, but I did not know that. So this is what I would have done differently, and that would have resulted in the correct answer. So for the group G and other users O, remove, which is a minus sign, write W, and execute X permissions. Go to GO-WX. To combine these two sets of permissions, we add a comma between them. So the final result is chmod U plus X, and then comma. I forgot that, but I got an error, so that helped me out there. And then you can combine them if they're going to be receiving the same permission changes. They're both going to get write and execute removed through minus sign WX, and then it will apply to this empty file. So got it right, but I misinterpreted the question. So hopefully the LPIC won't be like that. Hopefully it'll be pretty clear. But if it isn't, based on this question, I guess I should assume that what they mean is by everyone else, they mean the group as well. All right, so what would be the default permissions for a file if the umask value is set to 027? And I noticed that there's no the fourth one is missing, but it's probably just a leading zero. So my answer would be so it would be this. It would be dash 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 then it would be dash W dash, and then it would be uh, W RWX. So this is my answer. I'm sticking to it. Let's take a look. Now, hold on a second. For a file, see that? So this is what's going to get you during the exam. I changed my answer now, and it's going to be that because files won't have execute permissions granted to them. All right, so what would the default permissions for the file if the umask value is set to 0 to 7? So the permissions would be there. I got it backwards. It looks like this is actually backwards. Okay, so let's talk to the AI about this, if nothing else, just to use it as a therapist. Okay, so did it get it wrong too? Oh, really? Wow, okay. Wait, what? Okay, now I'm really confused. Okay. Okay, so here was my answer. Looks like I pretty much got it backwards. I thought each digit in U name from is it you mask from left to right responded to the permissions set, user group and others as it does for commands such as chmod. Okay, so here's my answer. Looks like I got it pretty much. I pretty much got it backwards. I thought each digit in umask from left to right corresponded to the permissions set, user group and others as it does. Okay, so help me, give me therapy. All right, let's hear what it has to say about this whole thing.
I see where the confusion came from. It's a common misunderstanding, but the umask value actually works differently than the chmod command.
That's
In
annoying.
umask value, each digit represents the permissions that are masked off or subtracted from the default permissions for a newly created file. The umask value is subtracted from 777 full permissions to determine the final permissions. The first digit in the umask corresponds to the owner's permissions. The second digit corresponds to the group's permissions. The third digit corresponds to others' permissions. So, in your original umask value of 027, the first digit, 0, means that no permissions are subtracted from the owner's default permissions, 777. The second digit, 2, means that right permissions, 2, are subtracted from the group's default permissions, 777. The third digit, 7, means that all permissions, 7, are subtracted from others' default permissions, 777. As a result, the final permissions for a newly created file would be: owner, 7, full permissions, 0. Group, 5, read and execute, 2. Others, 7, full permissions, 0. So, the correct final permissions would be 757, RWXRXRX in symbolic notation, rather than WRW-. It's important to remember that UMask subtracts permissions, while
Yeah.
CMOD adds or sets permissions.
Okay. Yeah, that is important. So I've got another question for it. That's annoying. Why does it work that way? Why hasn't that been changed in user-friendly distros like Ubuntu? Why keep setting people up for failure with this?
The way UMask works is a long-standing convention in Unix-like operating systems, and it has remained consistent for compatibility reasons. It might seem counterintuitive at first, especially for new users, but there are historical reasons behind it. 1. Consistency with POSIX standards. Unix-like systems follow the POSIX, Portable Operating System Interface, standards, which specify the behavior of various system interfaces, including file permissions. The UMask behavior is defined in these standards, and changing it would break compatibility with existing software and scripts. 2. Backward compatibility. Unix and Unix-like systems have a long history dating back to the 1970s. Changing something as fundamental as UMask would break a vast amount of existing software and scripts that rely on the current behavior. It's essential to maintain backward compatibility to ensure that older applications and scripts continue to work as expected. 3. Scripting and automation. Many scripts and automation tools depend on the current UMask behavior. Changing it could introduce unexpected consequences and security vulnerabilities in these scripts. While the UMask behavior might be considered unintuitive for beginners, it's something that users typically learn as they become more familiar with Unix-like systems. Moreover, user-friendly distributions like Ubuntu often provide graphical file managers and permission settings interfaces that abstract some of these complexities for the average user, making it less of an issue in everyday usage. Ultimately, the consistency and compatibility offered by the current UMask behavior outweigh the inconvenience it might cause for new users, and it's something that system administrators and experienced users have learned to work with over the years.
All right, so that makes sense. Get good. Okay, so there we go. Do this only using only a chmod command. Let me remember what I did. Okay, yep. So let's move on. So we're already at the next one. I just never changed it over. So the answer would be you subtract these from the default for the system, which I guess is 777. I don't even know. So it would be 750 is my final answer. So we're gonna have to. Okay, so it's definitely not a 7. This would be a 6, and then this would be a 4. So it's 640. Um. Why not? Why not? Oh, okay. I see. Because the UMass value is subtracted from the maximum permission set. And remember, files don't have execute typically. Um, at least by default. So directories always do. So the default permission set for directories is 777. For files, it's 666. And what UMask does is it alters the default setting by subtracting from the default 666 for files, 777 for directories, the values specified in UMask. In this case, 0, to 7. So what would the default permissions be for a file? That's key. That's essential to getting it right. So files don't have execute by default. So 666 is the default permissions. So it'd be 6 minus 0 is 6. It'd be 6 minus 2 is 4. And it would be 6 minus 7. Okay. I guess that would be -1. But I guess it just bottoms out to 0. So 6, that's the 4 on, the 2 on, and the 1 off. So that's RW0. The 4 is the 4 on and everything else off. And then -1, I guess it just bottoms out to 0, is everything off. All right, so the third guided exercise. Let us assume a file named test.sh is a shell script with the following permissions and ownership. Okay, so we're assuming that right now. What are the permissions for the owner of the file? So there we go. It's read, write, and execute. Using the octal notation, what would the syntax of chmod be to unset the special permission granted to this file? So we see there's a special permission granted here. And we're going to use the octal. So I believe that was the 2. So I think it would be this. It would be chmod, and then we're going to unset all special permissions. So that would be a 0. And now we just plug in the permissions we want otherwise. So we want a 7 for all them on there. Then I think we just want a 4, and then we want a 5. So I would go with 745. I could see an argument there for there being 755. I'm just not sure what they want to do with this after it's unset. Do they want it to have no permission for execute, or they want it to have execute instead? But this is my answer, and I'm sticking to it. Chmod 0745 and then test.sh. Okay, so what are the permissions for the owner of the file? The permissions for the owner, which is here, the second to fourth characters in the output of ls-l rwx. So the answer is to read, to write to, and to execute the file. Using octal notation, what should be the syntax of chmod to unset the special permission granted to this file? We can unset the special permissions by passing a fourth digit, 0, to chmod. Okay, so this is where it's a trick question. The current permissions are 755, kind of. No, they're not. They're 1, 7, 4, or 5. I'm not sure which one. So the command should be chmod 0755. So let me talk to the AI about this, get some therapy here. So is this kind of a trick question? Because couldn't answer be so is this kind of a trick question? Because couldn't an equally as valid answer have been chmod 0745 instead of 0755? How was someone to know whether or not to assign the regular regular X permission after unassigning the special permission based on the wording of the question. Based on the wording of the question. It seems like whether or not you get the question right depends more on how, depends just as much on how lucky you were to guess the intentions of the person who wrote the question without knowing for sure, as it depends on understanding Linux permissions. All right, so let's get some therapy.
You raise a valid point. The question, as presented, does lack clarity,
Thank
and
you.
the correct answer could indeed vary depending on the interpretation of the question's intent. It's essential in such cases to consider the context and clarify any ambiguities.
I am validated.
In standard Linux permissions, the octal notation used with CMOD typically includes 3 digits that represent the owner, group, and others' permissions respectively, while the 4th digit, optional, is used for special permissions. The common special permissions are setgid, setgid, and stickybit, each represented by different values, 4, 2, and 1, respectively. Given this standard notation, the most straightforward interpretation of unsetting special permissions would involve changing the 4th digit to 0, as that's how special permissions are typically removed. However, you are correct that without clear context, the intention could be open to interpretation.
Right.
In the absence of additional context, a response of CMOD 0745 could indeed be seen as a valid interpretation if the intention was to remove special permissions while leaving regular execute permissions for the owner intact. The interpretation may vary based on the expectations of the person asking the question. Therefore, it's essential to clarify the intent when dealing with questions that have multiple valid interpretations to avoid confusion and ensure a more accurate response.
So one thing to be aware of for anyone who hasn't taken like the CCNA, you can talk to them. So you have like a chat box you can use. They'll talk to you for sure the moment they can't see your entire face and all your shoulders and everything. So if you get something like this, maybe you can ask them about it. But yeah, it's just kind of a sad story question, unfortunately. All right, so got that wrong because it was unclear what they wanted to do with this setting once this one was removed. Like, it's unclear what it means to unset this. Does that mean that this will just be unset altogether, which is what I interpreted it to mean? Or does it mean that it would be set to execute? And the other thing is, this is a file. So it's an especially difficult question. If it were a folder, then okay, I'd admit, yep, deduct all the points from me. I'll put on my dunce cap and sit in the corner. Because folder, you have to have the execute in order to change into the folder. So the fact that this is a file means that I am vindicated and perhaps the smartest man in the world. All right, so moving on to number 5. Consider this file ls-l /dev/sdb1. So here we go. It's a block. What type of file is sdb1? It's a block file. Who can write to it? Only the root user. All right, so the first character in the output of ls-l shows the type of file. B is a block file, usually a disk, internal or external, connected to the machine. The owner root, and any users of the group disk can write to it. So I was wrong about that. Yes, the root can write to it, but it's not the only user that can write to it. All other users assigned to this group disk can write to it as well. 0 points for me. Moving on to the next one. So consider the following 4 files. All right, they've been considered. Write down the corresponding permissions for each file and directory using octal mode, using the 4-digit notation. Okay, so we'll do that in a file here. Okay, so another directory. So we've got a 7. First thing we need to do is check the special permissions for all of these. So this one does have a special permission. It has the sticky bits. These two don't, but this one does. So we're gonna have the 1 here, and then for the next ones, these will be 0, and then here we'll have a special permission. I can't remember if the 4 corresponded to the group or the user. I think the 6 corresponds to the group. So let's try this. Let's try it with the 6, but I could be wrong and it could be 4 instead. All right, so the next part are these sets of permissions here. They're all on, so they get a full 7. The next one, the 2's place is off, so it gets a 5. And then the next one, now this is tricky as well. I think because it's on, it actually gets a 5 as well. Because this was on. Like if it was a 4, then this would be absent. Even though you could assign it a T. So like all this does is flips whether or not this is a T or not, and then this means whether or not that T is applied. So this is whether or not you can apply a T, and this is whether or not you do apply a T. So if this were flipped to 0, then instead you apply the X, but it's flipped to 1, so now we're applying the T. But alternately, you can have the 4, and then even though you can apply the T, you don't apply the T. I think that's why the other one was the way it was. So I actually could tell the answer from that other one more clearly than I thought I could. All right, so this one's a lot easier. So it's going to be 0, 4, and 4. All right, so on to the next one. Now this is a directory, so it gets kind of interesting. The executes are all going to be on. So we've got a 7. And we've got the special permission for the group. And I can't remember if that's a 4 or 6. Let's go with the 6. Then we've got a 5 and a 5. All right, so here's my answer, and I'm sticking to it. Let's see if I got them right. We'll go right to the... so yep, it was the 2. It was the 2. You know what? It was the 2. It wasn't even the 6. I don't even know where I got the 6 from, but yeah, it was the 2. So I guess you can think of it kind of from. Oh, I guess you can think of it the same way, where it's like the owner, so like the UID, then the group, the SID. So it's kind of the same. Like the 4 applies to the owner just as it does up here, as to the group, and then 1 for the special sticky bits. Oh, I should be able to remember that it's a 2 going forward, but I got the 7 and the 5 correct. I got I actually forgot to do one of the files. I think I forgot to do this one, but I got the one I did. I got correct, and this one I got correct too. So the corresponding permissions in octal mode are as follows for another directory: 1755, 1 for the sticky bit, 755 for the regular permissions, RWX for the user, R-X for the group, and others. No write permissions. Then foo.bar, I got this one right as well. It's 0044. No special permissions, so the first digit is 0. No permissions for the user, --, and just read R-R- for group and users. Then the one I accidentally skipped, I don't know what happened there, is hugefile.zip. 0664, no special permissions. So the first digit is 0, 6, which stands for read, write, and then nothing, no execute for the user and group, and then 4 r dash dash for the others. Okay, and then the last one is sample directory. I almost got right, but I had that first digit. I didn't understand the numbering scheme for there, but I did understand you needed to set it to a special number. I just didn't know which number. But the answer is 2755, 2 for the SGID bit, which is this similar place you can think of it as for regular permissions. 7 RWX for the user, 5 R-X for the group and others. Alright, so explorational exercises. Try this on a terminal. Create an empty file called empty file with the command touch empty file. Now zero out the permissions for the file with chmod 000 empty file. What will happen if you change the permissions for empty file by passing only one value for chmod in octal mode, like chmod for empty file, and if you use 2, as in chmod 44 empty file? What can we learn about the way chmod reads the numerical value? So my answer is it'll apply it left to right. So like if you only have one, it'll only apply it to the user. If you give it 2, it'll apply it to the user in the group. And then if you give it all 3, it'll apply it to the last one to the others. So what it tells you is that it works left to right on the permission settings. But let's take it for a spin and see what the real answer is. Okay, so we're going to create an empty file. We already have one, so let's just blow away what we have. Okay, and then we're going to create one. So the UMask, we should see what it'll automatically get. It's a it's an empty file, so it'll have read, write, and execute permissions, and then the final execute, which will be set to a 7, will be deducted, so it'll be 774 by default. Let's take a look at that. Touch empty file, and then ls-d dl empty file, and there we go. Oh, I thought it would have 7. Oh, I got it. Wait, what? Oh, I got it twisted because no. See how I got confused? I thought I was creating a directory, so it would have been right if it was a directory, but no, it's a file. So I got confused. We don't need the -d because we're creating a file, and files don't have execute by default the way folders do. Okay, so now we're gonna zero out the permissions for the file. chmod 000 empty file. Perfect. What will happen if you change the permissions for empty file by passing only one value for chmod in octal mode, like chmod 4? Before we do that, let's do an ls-l on empty file. Okay, and now, so let's do an ls-l. There we go. So we got no permissions. That looks good. I just had a typo before that I corrected. Now let's do a chmod 4 on empty file. Okay, and then we'll do the same thing. Oh, okay. So I more or less had it right, but it looks like it applies it the other way. So let's add another one and see what that does. And it should fill out this one with read permissions now. All right, and I was right. So I was more or less right, but it goes the other way. So what we can learn about the way chmod reads the numerical value is that it reads it from right to left, essentially. It applies it to the other group first, then the group permissions, and then the owner. So remember that we zeroed out the permissions for empty files, so its initial state would be like that. Yes, and we see that here. Now let us try the first command, chmod for empty file. Yep, we can see it modified the others group first. See, the permissions for others were changed. And what if we try 2 digits, like in chmod for empty file? Now the permissions for group and others were affected. From this, we can conclude that in octal mode, chmod reads the value backwards from the least significant digit, others, to the most significant one, user. If you pass 1 digit, you modify the permission for others and then work backwards the more digits you add. With 2 digits, you modify group and others, and with 3, you modify user, group, and others. And with 4 digits, you modify user, group, others, and the special permissions. Key to know that. All right, so number 2, consider the permissions for the temporary directory on a Linux system /temp. Okay, so we can see it's got all permissions, and not only that, it has a special permission. Let's take a look at what mine looks like. Yeah, it looks like they left off the D. This is a directory, so I don't know. It seems like there's like a typo there, or either that or see. It's not that there's a file in there because this is a directory, so there may be a directory within this directory, but I think they just accidentally left off the D. Okay, so we can see mine has the same permissions, including the special permissions. User, group, and others have full permissions, but can a regular user delete any files inside this directory? Why is this the case? So a regular user cannot delete any files inside this directory, and that's the case because the sticky bit is enabled, and only the owner can delete any files within the directory as such. So /temp is what we call a world writable directory, meaning that any user can write to it, but we don't want one user messing with files created by others. So the sticky bit is set as indicated by the T on the permissions for others. This means that a user can delete files on /temp, but only those created by himself. Okay, so that's an important caveat. You could delete your own files that you create, but you can't delete any others. I'm not sure if the owner has special permissions in that regard, but yeah, I'm not sure about that. We can ask the AI. Let's ask the AI. Okay, so does the owner have special permissions in this regard so that even though the sticky bit is set and a user cannot delete any files except files they created, the owner still has permissions to delete any files they with, to delete any files they wish, or is it that the sticky bit permission changes apply to the owner and root as well? All right.
In the context of the sticky bit on a directory like /tmp, the owner and the root user do not have special permissions that allow them to delete any files regardless of ownership.
Okay.
The sticky bit permission changes also apply to the owner and root. So, even though the owner of the directory and the root user have full read, write, and execute permissions on the directory itself, they are still subject to the restrictions imposed by the sticky bit when it comes to deleting files within the directory. In other words,
I mean, that's all we really need to know. So, yep. So on to question number 3. So a file called test.sh has the following permissions. So dash, that means it's a file, and then it's got special permission here. And we know what this one is now. It's the fours place. So it's got 4, and then it's got 7, 5, 5, 4, 7, 5, 5. Meaning the SUID, instead of SGID, bit is set. Now run the following commands. There we go. So what did we do? What does the uppercase S mean? Okay, so we saw this with an uppercase T before. So it looks like what we did is we changed the we removed execute. So it looks like what I was talking about before, where when you have the special permissions bit set, that just says that when you apply the permission or you do not apply the permission, it applies the special permission. So you could still have, for example, the sticky bit set. So you would have a 1, and then you would have the rest of the 4 octal numbers that describe your permission sets. You could still have it so that you don't apply the sticky bit. So in that case, you would have a permission set of, for instance, 1, 0, 0, and then 0 again. To apply it, you would have to turn that bit on, so then you would have to have a 1 in the for the last number. So in that case, I believe what would happen is you would see the capital T. So what we did is we revoked what is typically execute permission, but in this case, it's that special permission of the SUID, which means that I forget, but the uppercase means that provision is deactivated. Lowercase means it is active. All right, so we removed execute permissions for the user who owns the file. The lowercase s or lowercase t takes the place of the lowercase x on the output of ls-l. So the system needs a way to show if the user has execute permissions or not. It does this by changing the case of the special character. A lowercase s on the first group of permissions means that the user who owns the file has execute permissions and that the SUID bit is set. An uppercase S means that the user who owns the file lacks, so minus sign, execute permissions. And and that the SUID bit is set. Okay, so you can have oh, that's interesting. Okay, so it didn't work the way. So okay, scrap that. Scrap everything I said. And let's look at these here. So this does not mean that remember what I said? I said this is the ability to apply, and then this is whether or not it is applied. Wrong. This is whether or not it is applied. If it's turned on, then a special permission is applied. But additionally, you can have the execute applied or not, but you run out of characters. You can't just add another character to your read, write, execute characters that you have. So you use a capital and a lowercase of the special permission to represent what typically would occur there. And if it is uppercase, it means that what typically would occur there is lacking. If it is lowercase, it means that it is present. Okay, so a lowercase s on the first group of permissions means that the user who owns the file has execute permissions and the SUID bit is set. An uppercase S means that the user who owns the file lacks minus sign execute permissions and that the SUID bit is set. The same can be said for SGID. A lowercase s on the second group of permissions means that the group who owns the file has execute permissions and that the SGID bit is set. An uppercase S means that the group who owns the file lacks minus execute permissions and that the SGID bit is set. It is also true for the sticky bit, represented by the T on the third group of permissions. Lowercase t means sticky bit set and that others have execute permissions. Uppercase T means sticky bit set and that others do not have execute permissions. So I got that completely wrong. Forget everything I said. The case sensitivity of the special permission determines whether or not the regular permission is present. If it is an uppercase, the regular permission is not present. If it is a lowercase, then the regular permission is present. And the regular permission is always going to be an execute permission because that's the space that special permissions occupy. All right, so thank goodness it's time to celebrate. Hey, keeping it under 2 hours too. That's great. So final explorational exercise number 4. How would you create a directory named BOX where all the files are automatically owned by the group users and can only be deleted by the user who created them? So you would assign it special permissions. You'd have to assign it 2 special permissions. You have to assign it the user special permission for the group, which is in the 2's space, and you'd have to assign it the special permission for the sticky bit, which is in the 1's place. So it would be 3. So you would use the special permission of 3, and then you would assign it whatever other permissions you would like. And since it's a directory, you have to have all executes. So it's going to be an odd number. So this is my answer, and I'm sticking to it. It could be any combination here, but the special character, whether or not that's a 3, is what really matters. Oh, this is kind of interesting. So this is a multi-step process. The first step is to create the directory, mkdir, BOX, lowercase o and x. We want every file created inside this directory to be automatically assigned to the group users. We can do this by setting this group as the owner of the directory, and then by setting the SGID bit on it. We also need to make sure that any member of the group can write to that directory. Since we do not care about what the other permissions are, we want to flip only the special bits. It makes sense to use the symbolic mode. That is kind of interesting. And this is interesting too because this lowercase s presupposes that there is a x there. Okay, but the first thing we do is you change the ownership group by using this colon and then saying we're using users. On the other side of the colon, that's the actual owner. So we're setting the ownership group by putting it to the right of the colon. Then we're applying that to the box folder that we created. And then we need to grant the special group permission to it, like so. So I was completely wrong, unless they're giving a octal way to do it. But yeah, I just completely biffed this whole thing. Note that if your current user does not belong to the group users, you will have to use the command sudo before the commands above to do the change as root. Now for the last part, making sure that only the user who created a file is allowed to delete it. This is done by setting the sticky bit, represented by a T, on the directory. Remember that it is set on the permissions for others, which is O. So there we go, represented by a T. And we're also granting execute, but it's a folder, so it needs that. There's no way not to grant it and have it work, because then you can't go into it. which might be what you want. You might want to keep people out of there, so that's always something to keep in mind as well. So the permissions on the directory box should be as followed. We have a special permission here and a special permission here. Of course, you can specify SGID and the sticky bit using only one chmod command with the commas here. So chmod G plus WXS and then O plus T. Bonus points if you thought about that. Well, I did not think about that. I thought about it in octal. No bonus points for me. All right, but definitely bonus points because I'm closing this out. Thank goodness, moving right along. So last section is the summary. In this lesson, you have learned how to use ls to get and decode information about file permissions, how to control or change who can create, delete, or modify a file with chmod, both in octal and symbolic modes, how to change the ownership of files with chown and change group, and how to query and change the default permissions mask for files and directories with umask. The following commands were discussed in this lesson. ls, list files, optionally including details such as permissions. Chmod, change the permissions of a file or directory. Chown, change the owning user and or group of a file or directory. Group, change the owning group of a file or directory. Umask, query or set the default permissions mask for files and directories. And this is a little bit misleading here because we're not setting the default permissions mask. What we're setting is a value to deduct from the default permissions. So in a way, you are setting the default permissions because after the deduction is made, those will be the default permissions. But the default permissions are created through a deduction of the values you specify in umask. So don't get that twisted. Don't think that you're setting the values that you use the numbers to. Remember that you are feeding it numbers it will use to subtract from the set of real default permissions, and therefore you create new default permissions that way, not by feeding it the default permissions themselves, but instead by feeding it the values it uses to make the calculation of the new default permissions by minusing the values you gave it from the old default permissions. All right, so that's it for this lesson. Thanks for watching, and stay tuned for the next one.